page 222, number 34. This is a Hess law problem for thermochemistry. The problem says to produce silicon used in semiconductors from sand, a reaction is used that can be broken down into 3 steps. The first step is SiO2 plus 2C yields Si plus 2CO. Second reaction is Si plus 2Cl2 yields SiCl4. And the third reaction is SiCl4 plus 2Mg yields 2MgCl2 and Si. Along with the 3 steps, you're given the 3 delta H values for each of the steps. Now, the first part of the problem, we're asked to find the thermochemical equation for the overall reaction for the formation of silicon from silicon dioxide, where CO and MgCl2 are byproducts. So by just first looking at this, the information we're given, we know that silicon is going to be a product, and as well as CO and MgCl2. So those are going to be our 3 main products, and then one of our main reactants is going to be silicon dioxide. In addition to silicon dioxide, we know that there has to be somewhere in the reactants where there's carbon and also magnesium and chlorine, as carbon monoxide and magnesium chloride are byproducts. So to find this final equation, we need to find this final equation by manipulating these primary 3 steps that are given. So to do this, we need to find which steps and compounds in these 3 reactions can cancel out, and then once those cancel out, we'll find our final equation. Now, there's only one. Now, the way you can cancel steps in this is you have to look for excess or like extra compounds or elements that appear on opposite sides of reactions that are also not necessary for the final equation. So, like I said earlier, in our final equation, we're going to have silicon, we're going to have silicon dioxide, we'll have carbon somewhere, and magnesium and chlorine. So those are those essential compounds or elements that will be in our final equation. But anything else that is not in the final equation can be excluded, and those will hopefully cancel out. So we're going to look for those compounds right now. So if we look at the first 2 steps initially, we can see that there are two elements right off the bat that appear on opposite sides of the equation. So that is silicon in the products of the first equation, and then also silicon again in the reactants of the second equation. Now you might be thinking that we shouldn't cancel these, as we need silicon in the final equation, right? But if you look to the third equation, you see that there's another spot where silicon appears in the products. So if we can cancel these, we can cancel these 2 silicons in the second and third equation and still be left with some silicon that will be produced later in the equation that does not cancel out. So those are our first 2 elements that will cancel. Now, if we keep looking for other elements that will cancel, if you see in the second and third equation, the products of the second equation, which is SiCl4, and the reactant of the third equation, SiCl4 is mentioned nowhere in the products of the equation that we're looking for, and it also appears on opposite sides of the equations. So that means it is non-essential, and it can also be canceled out. So if we cross that out there, we're now left with less product. We're left with less products for the overall reaction. So now, if we look at what we have left, we have SiO2, carbon, silicon, carbon monoxide, magnesium, chlorine, and magnesium chloride. Now, if you read again the information that we're looking for, each of these compounds and elements are the essential parts of this equation. So that means we have canceled everything that is non-essential, and now that we have just the essential compounds left, we can now write our overall thermochemical equation. So if you just take the product side, we can write it out. We have silicon dioxide plus 2 carbon plus 2 chlorine plus 2 magnesium for the reactants, and then on the product side we have silicon plus 2 carbon monoxide plus 2 magnesium chloride. So the overall thermochemical equation for the reaction is silicon dioxide plus 2 carbon plus 2 CO2 plus Mg yields silicon plus 2 carbon monoxide plus 2 MgCO2. All right, now if we can move on to the second part of the problem. Second part asks us what is the heat of formation for the formation of 1 mole of silicon. So to find the heat of formation for 1 mole of silicon, you want to think about that overall thermochemical equation we just solved for, but also we need to use the given delta H values. So if you look back at the equation we just found, we see the equation yields 1 mole of silicon, right? So, and if we also look at the delta H values, we see that, what you can do with the delta H values, if you add each of them together, you can find an overall delta H for the reaction. Now, in this problem, it won't be an issue as we do not need to change any mole ratios or flip any equations, but there are some problems where you'll need to, in order to keep the reaction balanced, you'll sometimes need to multiply a step by a number, and by multiplying that step, you'll also need to multiply the delta H value, but this is a simple problem, so each of the delta H values have remained the same. So if we add delta H1 plus delta H2 plus delta H3, we'll get delta H total, and that value is negative 592.7 kilojoules. Now for the final part, we're asked, is the overall reaction exothermic? Now to tell if as we learned earlier in the year, to tell if a reaction is exothermic or endothermic, all you need to do is look at the delta H value, and depending on the sign of it, you can tell whether it is exothermic or endothermic. Now as our total delta H value that we solved for in the past part was negative, we can conclude that yes, the reaction is exothermic because delta H total is negative. All right, guys, I hope that helped.